Multivariable Calculus, Section 13.1, Double Integrals and Volume. Let's review area under a curve in single variable calculus, and by under a curve we mean between the curve and the x-axis. So we start with an approximation using rectangles, and the sum of those areas is called a Riemann sum, and as the number of rectangles goes to infinity, the Riemann sum morphs into the integral. So the integral gives us the exact area between the curve and the x-axis. Delta x, discrete delta x, turns into instantaneous dx, and the individual heights of the rectangles, the function values, turn into every single function value along the interval from alpha to beta. So now we're going to talk about the volume under a surface, or in other words between a surface and the xy plane. What we do is we approximate the volume with rectangular solids, much like the rectangles, only they're three-dimensional. And as the number of rectangular solids increase, then the sum of those volumes approaches the actual volume underneath the surface. Sum of the rectangular solids morphs into the volume under a surface, meaning between the surface and the xy plane. So, for example, under this surface we have a rectangle which has an area, and then we could use any of the function values within that rectangle for the height of the rectangular solid. And so we add up the sum of all the little areas under the surface times the particular function value within that particular rectangular region. So now here we have another example, and what we're going to do to get the exact volume, we're not going to bother with any approximations, is we're going to integrate along the x-axis and then take that result and integrate parallel to the y-axis. And so our summation turns into a double integral over the region. The function values are the z-values, the heights of the rectangular solids, taken over the change in the area, and then that's broken up into two integrals so that we integrate the function values with respect to x from a to b, and then take that result and integrate with respect to y from c to d, where c and d are the endpoints along the y-axis. Now, it's interesting to note that it doesn't matter which order you do it in. So you work from the inside out. The first integral, you start with the x values and integrate treating y as a constant, and then whatever's left there after you plug in a and b for x's, you integrate that with respect to y. And that's going to equal the integral on the right, where you first integrate with respect to y and treat x as a constant, plug the c and d in for your y values, and then integrate what's left there with respect to x from a to b. Now, if the function values are all greater than or equal to 0, then our integral returns the volume between the surface represented by the function and the xy plane. Here's another example of that. Number 12, evaluate this double integral. Well, we start with the inside part, so we're going to integrate this with respect to x. That means we're going to treat y like a constant. So the antiderivative then is just 1/3 x cubed, keeping the y. But we still have the integral with respect to y to do later. So now we put the 2 and the 0 in and subtract, and we get 8/3 y, which is just a single variable integral now, and you integrate that and evaluate from 0 to 3, and you get 12. Number 18, another double integral. This time we start with the inside part, which will be integrated with respect to y, and so we treat the x cubed and the x as though they were constants. And we get 1/2 x cubed y squared minus 1/4 x y to the 4th. And we have to evaluate that from -3 to -1, and then we'll be integrating with respect to x. So we plug in the -1 and the -3 for the y values and subtract. And that's going to be integrated with respect to x, so we'll simplify it first, collecting like terms, and then take the antiderivative just the way we always used to, and finally evaluate from 1 to 3, and we get 0. This means that half of this surface is above the xy plane, and an equal portion is below the xy plane, and so the two volumes, the positive volume above the xy plane and the negative volume below the xy plane, must have canceled out. Now if you look at the original integrand, you can kind of see that there's some obvious symmetry here, and that's why we ended up with 0. Number 22, another double integral. We evaluate the integrand with respect to x, and so the e to the y remains as a constant, and we have to evaluate that from -2 to 2 and keep the dy, of course. So then we plug in the 2 and the -2 and subtract, simplify it, and we end up with a very simple integrand in one variable. And of course the antiderivative of e to the y is just e to the y. Plug in our 1 and our 0, and voila, the answer. Number 30, another double integral, and we're going to integrate with respect to y first. Notice that the first fraction is going to involve the natural log of y, and the second fraction we're going to use 1 over x is just going to be treated as a constant, and so we'll take the antiderivative of y. So we get x log y plus 1 over x times the antiderivative of y, which is just a half y squared, from 1 to 3, and keep the dx. So then we're going to plug in the 3 and the 1 and simplify that. Simplifies rather nicely. And now we're going to integrate with respect to x, and so we get a half x squared times log 3, and then 4 natural log of x. And notice we're not using log of the absolute value of x because all the values are positive, so we can just skip that. Evaluated from 1 to 2, we plug in 2, we plug in 1, and then we rearrange all that with our log laws. So we get log of 3 squared plus log of 2 to the 4th, and then we can collapse that, make that times, and also divide by the square root of 3 for that last log. So we end up with the natural log of 48 square root of 3. Number 32. Show that the double integral over a certain region of f dy dx is equal to the double integral over the same region f dx dy. So in other words, you can switch the dx and the dy and still get the same answer, and we're going to do it for this particular function. F of xy equals sine x cosine y, and the region is x is going from 0 to pi, and y is going from negative pi over 2 to positive pi over 2. So I'm going to start out with the first one, where we integrate with respect to y first, and that means that we treat sine x as a constant, and the antiderivative of cosine y is sine y. We're going to evaluate that from negative pi over 2 to pi over 2, and then integrate with respect to x. So we plug in our values, and sine of pi over 2 is 1, and sine of negative pi over 2 is negative 1, so when we subtract we just get 2 sine x, and the antiderivative of that is negative 2 cosine x, which we then evaluate from 0 to pi, and we get 4. So now we're going to do it the other way around and integrate with respect to x first, treating cosine y as a constant, and the antiderivative of sine x is negative cosine x. And we're going to plug in pi and then 0 for a negative cosine x, and when we subtract we get 1 minus negative 1, so we get 2 cosine y dy, and the antiderivative of 2 cosine y is 2 sine y, which we then have to evaluate from negative pi over 2 to pi over 2, and sine of pi over 2 is 1, sine of negative pi over 2 is negative 1, so again we get 2 times 1 minus negative 1, which is 4. So both ways give us the same answer. So now it's your turn to do some double integrals. Have fun!